last class, we introduced this idea of numerical predictors. So this is what we did, right? We used to live in a world of univariate models, so intercept-only models. This was all of part 3. We introduced these big ideas of sampling variation. So every time we take a sample, we get a slightly different sample, even though it's drawn from the same underlying distribution. So we introduced the ideas of sampling variation. We simulated the central limit theorem, which gave us a known sampling distribution even when we don't observe the underlying population distribution. And this was the big idea, right? It's like, even though we don't observe the underlying population, what we do know is the distribution of the sample means. That was all of part 3, essentially. So you just demonstrated to me that you sort of have some conceptual mastery of that material. So thinking about the sampling distribution and the population distribution and how they relate to each other. Then we built up this idea of an intercept-only model, where not only do the sample means follow a known distribution when our sample size is large enough, but when we're building statistical models that look like this, where we're just predicting the outcome variable using an intercept only, building these kinds of statistical models where we minimize the mean squared error, this gives us a distribution of model parameters that follows a normal distribution, or approximately normal distribution. Last class, we introduced this idea of including a predictor variable. So not only are we working with an intercept, but now we're also introducing this idea that maybe these two variables are related to each other, and we want some way of building statistical models to check for the presence of a slope relationship between a predictor variable and an outcome variable. And we walked through this whole setup where everything we're doing essentially is the same except extended into 2 dimensions that we did in part 3. So this was the basic idea. We, instead of just picking the intercept like we did in part 3, now we're picking the slope. So we can move the model up and down, we can pivot it, and those are our 2 sort of levers of control. So we have these 2 ideas, moving these 2 things around, and all we're trying to do is pick the model that minimizes the mean squared error. So this is just our picture. We can move the slope around, and we can minimize the mean squared error. So this was the basic idea, which allows us to build statistical models on every sample we draw. This was the picture I wanted you to have in your heads from last class. Here, you'll remember I drew 8 different samples. Each one has a slightly different data set, simply from sampling error. So every time we draw, we get a different data set. And each statistical model I built with those 8 looked slightly different. Each one has a slightly different slope, but each one of these models is the best fit to the data. One of these has a negative slope, the rest have positive slopes. And the question we might ask is about inference, using the sample that we drew, making claims about the unobservable population slope. Like, is there a relationship here? So this is the distribution of all model slopes. So I drew 1,000 observations and built 1,000 statistical models and plotted the distribution of slopes. The true parameter, so the true slope for the population is right here at 0.01. And then you can see, just simply due to sampling error, some of them are very large, so very strong positive relationships, and some are very small, so very close to 0. Some are even negative. So this is the distributions. So we're getting very different slopes simply due to sampling error. And the question just like in part 3, we were asking was whether there's whether we can find a true slope simply using our sample. So, is there a positive relationship between these the two variables? And this essentially boils down to a t-test, just like we did in part 3, but instead of focusing on the intercept parameter, we were focusing on the slope parameter. But really, everything else is exactly the same as what we did in part 3. It's just now we're looking at relationships between variables, which we can capture in our beta 1 model parameter. So we're extending this from one parameter into two parameters, and both of those parameters are doing the thing that we were doing in part 3. So here, this is just a picture to remind you that we don't observe those 1,000 samples, we just observe one. So you're going to collect a data set, you're going to observe one sample. That's all you get. We don't see the actual true distribution behind what we're doing. So I faded it out just like we did in part 3. We see this one, and we see the sampling distribution. We see the sampling distribution not because it's observable, but because it's theoretically given to us by the central limit theorem. Without it, we couldn't really do this. So we have the sampling distribution, we have our sample slope. And then, just like we've done a couple of times already, we center the sampling distribution on our null hypothesis. So when we're dealing with relationships between variables, our default null hypothesis is 0, which is essentially telling us, our default null hypothesis is saying, there is no relationship between the variables. So we have our default null hypothesis of no relationship between the variables, and then we check the probability of seeing a sample slope as extreme as the one we do, which gives us the p-values. So what's the probability of seeing something as extreme as what we do under the assumption that there is no relationship between the variables? And that gives us our p-value. This is what we call the default null, which is baked into all of our regression software. All of our statistical packages assume our null hypothesis is that there's no relationship. Okay, so nice. This is the picture. And the p-value tells us essentially the surprisingness of our sample. Under the null hypothesis, how likely is it that we would see something this extreme? Okay, and then this is the picture I showed you, and you said you didn't like this. And I said, I like it, and I'm still going to keep it. This is a picture of the p-value. So we have all of these sample slopes from lots and lots of repeated draws from the null distribution. So these are the slopes you would see if the null hypothesis were true. But what we actually see is this red one. This is our sample. So the question is, does it look like the sample was taken from one of these null slopes? And the answer for me is no. This is a visualization of the p-value when it relates to slope parameters. Yeah, James.
You said it looks like it did not come from one of the null slopes? But how come? I don't understand that.
Yeah, so I think there are very few null slopes that look this steep. So if I were just randomly picking one of the gray ones, what's the probability I would select something like the red one? And I would say there's not really any that look that steep. Which tells me it's very unlikely that those are the slopes that we're drawing from. So the null hypothesis seems to not generate slopes this steep very, very often. Yeah, good question. So then we walked through this happiness per capita and GDP model where we went through and fitted the relationship between life evaluation across a bunch of countries in 2024 and GDP per capita. We did this in logs. And then we walked through model predictions. So this was the fitted model, and then we were just going through and making predictions. If this feels like high school algebra, that's great. It basically is high school algebra. We're just, general linear model is not much more complicated than your high school algebra. And the good news is 95% of the main results you see in science are no more sophisticated than these kinds of models. Okay. It's not like there is that 5%, so if you go on to do more science, you will need more than this. But this is the basis of most of the models we actually run. Yeah, Courtney? So the way we find model predictions, we plug in the value we're trying to predict for. So if I'm trying to find the wait times at 100 minutes after open, I just plug in 100 into the model, and it gives me the average wait time at 100 minutes after open. And then we just walked through and calculated a couple predictions. I think that might have been where we left off. I think we didn't get all the way through the exercise, is that correct? We did not. So I'm going to leave this as an exercise for you to go back and continue. I think for the sake of time, we're going to work with our exercise for today. The prediction at two different values, we said we have a prediction at 200 and a prediction at 100. What happens to the wait time? Like, how does wait time change when we increase on the horizontal axis? I think we did talk about the difference in life evaluation as we increase 1 unit on the horizontal axis. The change in the vertical axis for every 1 unit change on the horizontal axis is exactly beta 1. Beta 1, the slope, tells us how much does the vertical axis change when we change the horizontal axis by 1. So this is a picture of changing by 10, but we walked through the exercise for the interpretation of 1 unit in the exercise. Okay, so this is where we've come from. We said we're introducing a numerical predictor in addition to the intercept-only model, which the only difference is that now we have a beta 1 times some predictor variable. We're just fitting using a predictor variable, which gives us a slope. What we're doing today is introducing a predictor variable that's now categorical. And then in part 5, we're going to introduce control variables, which I'm incredibly excited for. So that's our little speed run through what we did last class. What we're doing today is making an extension. And I think in a lot of ways, if we've done our work properly up to this point, what we do today will feel like almost a trivial extension of what we've done. We have the groundwork laid for really all of the extensions we're about to do the rest of the semester. Like, everything is just a simple tweak to the equation. In part 3.4, we did this paired t-test, where I went out and collected wait times in the morning, and then to the same restaurant, I went in the afternoon and collected the wait time in the afternoon. You remember this? This was, unfortunately, no one paid me to go get lunch and breakfast at a restaurant. This was simulated data, unfortunately. But this was the setting we used in part 3. It was like, we're just going to check whether the average was some value. And in part 4.1, which we just quickly recapped, this was introducing a predictor variable. So instead of comparing morning to afternoon, I'm just looking at whether wait times increase as the day goes on. And this was the model. We had an intercept, so we needed the intercept still, but then we also had some slope component. What we're doing today is thinking about a third environment, where we have 2 categories. So our running example for today is going to be neighborhoods. So one question people have in sort of urban planning circles is whether green space is related to temperature. So we live in a city, sometimes it gets hot in summer, and trees are really nice for a lot of reasons, but one of them is that it keeps it cool. So we have this data set on neighborhoods and average temperature on the vertical axis. And I have 2 groups. One group with lots of green space, so there's like a park in the neighborhood, and then one group that does not have a lot of green space. So there's no meaningful parks in the neighborhood. And the question is whether there's an actual difference here. So like, do neighborhoods with green space have lower temperatures? Looking at this data, it just visually, it looks like there's a difference. But even though that was enough for the first part of the semester, what we're working on now is actually testing, not asking are there differences in our sample, but is there a difference in the population? So we're making inference from our sample about the population that we do not observe. So our question is not, do neighborhoods in our data set with green space have lower temperatures? It's, do neighborhoods with green space in general have lower temperatures? And that's not something we can see with our data set. So the good news for today is we have basically all the tools to answer this question without a lot of extra work. And essentially what we're going to do is extend this environment into this one, except the horizontal axis, the predictor variable, is now categorical. Okay, and how many of you have run a two-sample t-test before? Okay, a few people. If you've seen a two-sample t-test before, we are doing a two-sample t-test today, but just in a much more elegant and general framework that we can then extend later. Okay, so here's our setting. My first question for you, so vertical axis is our outcome variable, which is average neighborhood temperature. Horizontal axis is neighborhood green space, so whether the neighborhood has green space or not. I want you, as our first kind of warm-up question, this may seem obvious, maybe it doesn't. Tell your neighbor they did great on the mini exam. You weren't looking, but they did great. And then tell them what variable type neighborhood green space, what variable type neighborhood green space is. And don't just give me both the big category and then also what the subcategory is. We'll take a minute here. Your neighbor did great.
Okay, so based on y,
Understandable. Okay, sorry to interrupt your lovely conversations. So what is it? What's the variable type? Yeah, Jackson.
Binary categorical.
Binary categorical. We have two separate categories. And those categories are high green space or low green space. I've written these out as yes and no. So is there green space? Yes. Is there green space? No. I've also labeled them as 0 and 1. So you may remember this from the beginning of the semester. Sometimes we record categorical variables with numbers. So sometimes we could just record this as, you know, the values in the cells. We could record it as high green space and low green space, or we could record it as yes to high green space or no to high green space. But we can also record it as 0 and 1, where 1 would just correspond with yes and 0 would correspond with no. So that's what I've done here, which just organizes a binary categorical variable as two numbers on the number line as a predictor variable. Once we have this, we are almost all the way done. So I have 0 and I have 1. These are just, this is a strip plot, so there's some jitter horizontally just so we can see the data. But this changes our question from is temperature lower in neighborhoods with more green space to does temperature change as we increase by 1 on the horizontal axis? So if you're thinking about our general linear model framework, introducing a slope parameter as we move horizontally on the horizontal axis, what happens vertically? We can reframe our original question in this way. Okay, any questions here? So this is the equation we're going to use. We have temperature, which is our outcome variable. We have a beta 0, which is our intercept parameter. We have beta 1, which tells us what happens to green space as we go from 0 to 1, just like we did in part 4.1. And then we're just going to multiply it by our categorical variable, which we've coded as 0s and 1s. So we've turned a categorical variable into numbers, which are not meaningful numbers, but they are numbers, which allow us to move on the horizontal axis, going from 0 to 1. So this is not a numerical variable, but we can record a categorical variable, particularly a binary categorical variable with numbers like this. Okay, so the important thing here, the general linear model framework, it doesn't matter. It doesn't care whether the predictor variable is categorical or whether it's continuous or numerical. If we code our groups as 0 and 1, we can use the same model to form our statistical model. That's the big idea. Yeah, Erwin.
So, if there's more categories, will we more than 0 and 1?
Yeah, this is a good question, and it's a little bit outside of what we're doing in part 4, but it's a good enough. It's a great question and relates to what we're doing. The question is, what if we had more than 2 categories? How would we encode this? And there are kind of 2 ways to encode more than binary categories. We could encode it as 0, 1, and 2. The problem with this is the intervals between 0 and 1 and then 1 and 2 mathematically would be the same. Right, just on the horizontal axis, each one of the intervals would be equal. And with categorical variables, we don't actually, the intervals are not meaningful. So what we'd be doing is forcing meaningful intervals on something that actually isn't meaningful. So the more correct way of approaching more categories than 2 is to actually break it out into more than 2 variables. So you could say very low green space, or no green space, yes or no. Medium green space, yes or no. And then high green space, yes or no. That would mean we would have 3 predictor variables, which we'll come to this eventually. Right now we're focusing on binary categorical variables as the simplest case. Does that answer your question? Yeah. Nice, great. Love that question actually, that's a really good one. Anything else? So nice. So binary categoricals, and then exactly like with numerical predictors, the general linear model is just giving us a beta 1 that gives us a slope, and it tells us the probability of seeing this slope if there were no actual relationship between the 2 categories. Okay, so from here, we're basically done. You like how quick this is? Okay, so this is our model. We should talk about interpretations, but this is what the model is doing. It's saying we're going to set an intercept, which gives us an intercept at 0. So the model prediction at 0 comes from the intercept. It gives us a slope as we go from 0 to 1. which is telling us how much temperature changes when we go from no green space to high green space. And then that's about it. So we're going to spend some time with the interpretations. So we've introduced how to interpret beta 1 and beta 0. But I'm looking for what beta 0 means in this case. So we built this model. Use your knowledge about general linear models, what the intercept tells us, to answer this question. This is for sure going to be a mini exam question or something like it. What does beta 0 tell us here? Turn to your neighbor, tell them a wild guess for the interpretation, and then when your neighbor does that to you, correct them sternly. Yeah, that's true. I did tell you that.
That's what I'm saying. He said, you know, you can be friend James, he be in class, and he just be yapping, so I want to make sure.
Also true. Okay, great show. Someone want to interpret beta 0 for me? All right. Is that a hand?
Yeah.
Okay.
The average temperature of the cities without green space.
Perfect. The average temperature of the neighborhood is coded as 0. So the average temperature of the 0 group. That will always be true. No matter how we've coded this, we could switch the coding, have yes be at 0 and and no be at 1. However we code it, the interpretation of beta 0 is the average vertical axis, in this case, average temperature for the 0 coded group. This is also the interpretation of beta 0 in the numerical predictor case. It's just the average vertical axis at a horizontal point of 0. So when x is equal to 0, what's y? That's just what the model tells us. All right, any questions here? What about beta 1? Someone interpret beta 1. Interpret beta 1 for your neighbors. And then I'll have someone tell me.
It's the average, you know.
All right, someone want to answer my question? James.
I said it was the average change in the vertical axis.
The average change in the vertical axis as we move between groups. Yeah. So the average difference between the 0 group and the 1 group. Yeah. Lots of different ways of saying it. It's essentially just the slope of our equation. Okay. So cities with green space have a temperature that's lower by exactly beta 1 on average. Okay, and then the last thing here So I've plotted the average for the 0 group. I've also plotted the average for the 1 group, which is the 0 group plus the difference between the 2 groups. So in this case, beta 1 is negative, so that gives us a smaller average for the 1 group. But if we had recoded it so that 0 was the high green space group, this would just be the average for the high green space, and then it'd be a positive slope. The numbers would all be the same. It's just the interpretation, the specific interpretation of the numbers would be different. Okay, any questions? So it doesn't matter which way you set 0 and 1, as long as you're setting up the model and then interpreting it according to how you've set the model up, you'll get these numbers. Okay, very nice. So the last thing we're going to talk about here is just to remind you, whenever we're dealing with samples, we are dealing with sampling error. So I ran, this is the 3rd time I'm showing this kind of figure. I have 8 different samples, each drawn from the same underlying distribution, each showing a model estimating the relationship between green space and temperature between the groups. And each one, just like in the last 2 cases, part 3.4 and part 4.1, we have different sample slopes. So the sample parameter we're estimating in each one of these 8 different samples is slightly different. It's a little bit hard to see in this case because the sample size is large, but each one of these sample slopes is slightly different. This is just to remind you that when you collect your data, you're only going to see one of these. And if I'd run 1,000 of them, we'd get a distribution of sample slopes, the difference in average temperature between the yes and the no group. But we only see one observation. So we don't see all of those 1,000, we just see the one. And amazingly, from the central limit theorem, we also get the sampling distribution. So if it feels like I'm repeating myself, it's because I basically am. We've done this 3 times already. Once in the intercept-only model. Second, when we introduced numerical predictor variables and we were talking about the distribution of sample slopes with a numerical predictor. And third, now, when we have a binary categorical variable. The distribution of differences between the groups follows a known distribution given to us by the central limit theorem. What's amazing is we have these 2 things, and this is enough to make probabilistic claims about a null hypothesis. So just like we do, we center the sampling distribution in green on our null hypothesis, which our default null hypothesis when we're dealing with relationships between variables is 0, so no relationship between variables. So in this case, we're saying the null hypothesis is that the 2 high green space and low green space neighborhoods are not different. And then we're just checking from that null distribution, what's the probability we see something as extreme as what we do? And then we find the probability in both tails. So here, this looks very extreme. Our p-value is so small we can't even see it. This is the process. No matter what parameter we're looking at, building our statistical models, as long as our model is well set up, this is the process. This is how we set up our null hypothesis, our sampling distribution, and then we draw one sample from that underlying population distribution and make probabilistic claims about the null. Okay, so very nice. P-value, just like before, surprisingness of the sample if the null hypothesis is true. This is the probability of seeing the sample by chance if there is no difference. It's under the null hypothesis, and we can't make claims the other direction. We can't make claims saying the probability that the null hypothesis is true. We can't go that direction. It's centering the sampling distribution on the null and then making probabilistic claims if we're drawing from that null distribution about the probabilities we're seeing our sample. It's a little outside the scope of what we're doing in this class, but there's a very good reason why we can't go the other direction. We can't say what's the probability our null hypothesis is true. You need a whole extra branch of statistics to be able to do that. We almost never do it. So then we say a small p-value is strong evidence against the null hypothesis. So in this case, the null hypothesis and the sample look incompatible. They don't look like they belong together. Okay, any questions here? If it feels like I'm repeating myself, it's because I basically am. If you see this framework, and as we build the rest of the framework up, I'm training you to see the same pattern in increasingly complicated models. Okay, so this is the distribution of sample slopes under the null hypothesis of no difference between high green space and low green space neighborhoods. If the null hypothesis is true, these are the slopes we're drawing from. We're just randomly picking one of the slopes, and I would say this is very unlikely to be drawn from this pile. Think of it like, you'll play, what's that game called where you like, you pile the sticks up and then you try to like pull them out? I grew up in an analog world, barely had a computer growing up. Those are the games we played. Okay, how nice. Do y'all like this figure? I'll take that as a no, because it's more fun. I love this figure and I'm gonna keep it, even though you don't. Okay, so this is essentially the way we set up tests of differences between groups. You may have seen this in your statistics class as a two-sample t-test. So we're checking the difference between groups. Under the hood, the two-sample t-test mathematically is doing exactly what we just did. It's just checking whether the means are different. What we're doing is building a more general model, which captures the one-sample t-test, captures ordinary least squares or regression, and it captures a two-sample t-test. It also captures ANOVA, the analysis of variance, among many other things. The model we're building is a very general model, as you can tell by the name. The name is very descriptive. It's both general and linear, and it's a model. So what we've done so far is talk about numerical predictors and categorical predictors. After we get through some of the nuances with how we sort of evaluate how good these models are, next week, we're going to talk about control variables in part 5. So that's where we're going. Unfortunately, I've been talking too long. I think we have an exercise, but I think it's better if we just don't start this today. We start it next time. I'm going to give you 5 minutes. I don't expect you to be able to give this back to me. I'm not going to hold you after class generally, but there's not enough time to do what we want to do. So take a look at exercise 4.2, and we'll start that next class. Congrats on the mini exam. Treat yourself nicely, and I'll see you on Tuesday.